Ignore this monitor. All right. Hello, everyone, again. So welcome to lecture 4 of online learning, games with electronic markets, applications and operations, etc. So today we are going to kind of continue the plan that we started in lecture 1. And this lecture would be a wrap up to the first half of the course that we will think about full information online learning. And the key player of today's lecture is essentially online convex optimization. And I'm going to use the abbreviation OCO. So here is the plan. So we are going to start revisiting Blackwell approachability, which was this powerful tool that we learned throughout the course. I mentioned an algorithm for solving Blackwell approachability. I never actually analyzed that. Then I realized it's actually going to be very well connected with what I'm going to cover next. So I'm going to actually show you that analysis, the one I promised to post on Canvas. So you're going to actually see that in the classroom today. And then after that, we're going to rethink, so revisit Blackwell approachability again, and think about whether we can reduce this problem to something more general. And that's going to be online convex optimization. So I'm going to tell you what the setup is, and then I'm going to show you how you can actually reduce Blackwell approachability to online convex optimization using what I call the primal-dual algorithm. And then the next half of the class, I'm going to tell you how you can solve online convex optimization by introducing not like a series of algorithms that people usually think about in online convex optimization, but actually introducing the mother of all first-order methods, thanks to seminal work of Nesterov, called online mirror descent. So I'm going to set up the stage for introducing online mirror descent by recapping a lot of the stuff from convex analysis. And then I'm going to tell you what the algorithm is, how you can interpret that as actually a gradient descent space algorithm, but in the dual space. And then we are going to finish the lecture by analyzing this algorithm, getting some regret bounds, and seeing that we exactly match the direct algorithm up to some constant. It actually has, this one has better constant. All right, so this is the review of today. But before getting there, I want to also recap what happened in the first half of the class. So this is the DAG of our classroom, the first half. All right, so this is us. We entered this DAG. In the lecture 1, we learned external regret, how can design algorithm for that. If you remember, we talked about the best expert problem, and then we realized you can use multiplicative weight update to get external regret, right? And then starting from lecture 2, we thought about how we can get stronger notions of regret, so that if we use them in games, then agents are using those learning algorithms, we converge to correlated equilibrium. So there was a reduction from internal regret to external regret. That was the Blum and Mansour paper. We also saw that if you have just external regret learning algorithms as agents in the game, they're going to converge to a weaker notion of correlated equilibrium called force correlated equilibrium. But then by that reduction, you could get internal regret. And now if your learning agents are running internal regret learning algorithms, no internal regret learning algorithms, you're going to converge to correlated equilibrium. And then we introduced Blackwell approachability and talked about how you can actually get learning algorithms with no external regret or no internal regret using Blackwell approachability. Then in lecture 3, we talked about the different setup, which was decision maker listening to a forecaster. And in particular in games, when learning agents are listening to a forecaster about other players in the game's strategies. We talked about noisy forecast, how you can use some sort of follow the perturbator in order to create forecast for a learning agent. And that was inducing the external, no external regret learning behavior. Then we introduced the notion of calibration forecast. And from that, we could get behaviors on the agent side that had no internal regret, therefore convergence to correlated equilibrium. And then finally, we talked about how we can have calibration in forecast using Blackwell approachability. Right, so this is basically what happened in lecture 1, 2, and 3. And then I promised you that Blackwell approachability is connected to more general, probably typical tool for computer scientists and dependent operations, and that's online convex optimization. And today's lecture is really about this connection. So if you look at this tag, this is the super source. So there is a path from OCO to every single thing that you see here, essentially, like the ones that are results, like accelerated equilibrium. So this is going to now wrap up the first half. Like if I can show this connection, that basically, well, so first of all, I can design an algorithm for OCO, and second, I can reduce Blackwell approachability to OCO. Then we can just like focus on online convex optimization. And then in the next half of the class, not today's lecture, in general the class, I'm going to talk about relaxing the full information assumptions. We're going to talk about partial feedback, we talk about bandit feedback, we talk about graph feedback, etc. But today, still, we are going to stick to the full information set. We just generalize the reward function to be, or the cost function to be a general convex function, all right? So let's just start from recapping what Blackwell approachability was. So recap, for those of you that probably have forgotten, this is the setup for Blackwell approachability. We have two players playing a sequential game. Let's say player one is selecting a strategy XT at every time t, that is in set curly x. YT is selecting a strategy in the set curly y. And think of these sets as being maybe convex and compact. And then the game is endowed with a target set S, which is also convex and not necessarily compact, but it needs to be closed. And also there is a utility function U, which is a vector function that maps a pair of strategies in X and Y to a d-dimensional vector. And in particular, I made the assumption that, first of all, U of X and Y is always, say, in a ball of radius 1, L2 ball of radius 1 around 0. And also importantly, U is a biaffine function, which means if I fix X and I look at Y, it's going to be an affine function of 1 and vice versa. Right? So they play a sequential game as we described. The goal of player one is minimizing the distance of the average payoff with target set S, and the goal of player two is maximizing that distance. Then we talked about the notion of half-space approachability. Let me define that. So definition. Target set S is called half-space approachable if for every half-space H containing S, there exists a strategy, I'm going to call it X superscript H, such that the utility of X superscript H and Y is always in H, regardless of what the adversarial is, but regardless of what player two is. All right. This is what we call half-space approachable. Then we have this other definition, which was the actual definition of approachability. So a target set S is approachable if the following is true. If there exists an online algorithm generating sequence, let's say x1 to x capital T, all of them in X, against approximately adaptive adversary generating the sequence y1 to y capital T, such that if I look at the distance, let's say the L2 distance of my average payoff, 1 over T summation T from 1 to capital T, u of x and by T, with set S, this will be, let's say, at most G of T, and the limit of G of T as T goes to infinity should be equal to 0. Right? That's the definition of the half-space approachability. This is the definition of approachability or Blackwell approachability. And then here's the theorem that now we're going to actually prove. The theorem, Blackwell approachability, target sets S, and every time I say a target set S, you should really think of it as a convex and closed set. Okay. All these criteria, they are satisfied throughout. The target set S is approachable if and only if S is half-space approachable. All right. In particular, moreover, if we have what I call query access or Oracle access, maybe Oracle access is a better word. We have Oracle access to XH for every half space containing S, which means you pick your half space that is containing S, and then I can come up with this strategy, this very powerful strategy for pointing to that half space that regardless of what layer 2 does, the utility lands in H. So if you have Oracle access to that, there exists a polynomial time algorithm such that G of T for that algorithm is order 1 over a square root of T. Let me add one more assumption to my setup. So not only set is convex and closed. Yeah, so let me add an assumption just for making my life easier, that S is also a subset of L2 all, although I'm not sure if I really need this assumption. I don't really need that assumption, but let's add it in case that it can help us. Right. Yes.
I have a kind of conceptual question. What is the key difference between half space or like the set S such that we know forcibility is equivalent for the half spaces by
So this is a very strong statement. So you're saying there is a universally good strategy such that there is a wide.
That's forcibility, right? The half space forcibility.
Right.
Yeah.
So you can't hope to have that for a target set S. It's too good to be true. Because if that is the case, I should not even think about Blackwell approachability. I should just go with that strategy all the time. But the point is that the strategy.
If there is any intuition behind what's different between half space.
Why half spaces are easier?
Yeah, why half space?
You already saw a lot of examples of that, right? So
yeah.
When we talked about external regret, internal regret, we checked the half space forcibility, and it was kind of clear. But think the intuition is, not sure really if I can give you a good intuition. There are some intuitions that will be clear when I talk about the reduction from uneconomic substitution, but I think that's the best intuition I can tell you. And for that, you should wait until I get to that point. Right, somehow the half spaces that, or hyperplanes that are tangent to convex sets are defining the convex set. So I only need to worry about those and problem in the dual space. You will see that kind of in this guide when I talk about the reduction. Other than that, I don't think there is a better intuition. Right? So I'm going to prove this theorem. In particular, I want to show that the harder direction, that if S is half a space approachable, then it's going to be approachable. All right? And the proof is very constructive through an algorithm. All right, so here is an algorithm. An algorithm that is going to solve Blackwell opportunity, and we actually talked about. Let me recap what the algorithm is. It has a very clear geometric interpretation. So this is what the algorithm does. So let's say you have this target set S that you want to get close to. And say you are some iteration. So you have a vector U bar, let me call it U bar T minus 1, which is your average vector up to this iteration, right? So if you're outside of this S, you're eventually going to get closer. So here's what you might want to do. So I'm going to project U onto target set S. So I get a point, which I'm going to call it pi of, or pi S of U bar T minus 1. So think of it as L2 projection of U bar on S. Now, well, so let's think about the half space that passes through this point and separates U bar from S. Basically, the tangent, the half space defined by the tangent hyperplane, right? So look at the hyperplane with the normal vector, which is this vector, that contains this. So I cannot get necessarily close to S, but I know I can actually get close to this H because of the half space forceability. And not only I can get close on average, I can actually get close even in this very iteration. So now a natural strategy would be once you identify this half space and call it HT, I'm going to play X of HT. And because of that, you know, what happens is that regardless of what the adversary does in that round, your utility, the new utility for the point xt, so this is xt, for the point xt that you're playing, regardless of what the adversary does, is going to be somewhere. It's not necessarily in S, but it is definitely in H. And then you're hoping that, well, so this is kind of like an improvement towards getting close. And it is indeed an improvement, and we're going to show that for. So that's kind of like the intuition. Let me write down the algorithm. So I'm going to start with, say, some point. So you may go with the notations in my notes. Right. I'll use 0 or to be O0. So we are taking out d-dimensional space. Now for t from 1 to capital T, now do the following. So if U bar T minus 1 was in S, then you're good to go. Just play an arbitrary strategy. X in S, it doesn't really matter. So this is the case that this is already in S. Otherwise, do exactly what I mentioned. Project U bar T minus 1 onto S. So that's going to give us the projection phi S of U bar T minus 1. Consider half space HT So what is this half space? It is a half space in the d-dimensional space. The normal vector imagine is this, that is in this direction, which is u bar minus pi of u bar. So it's something like z bar. Well, so the actual normal vector should be in the other direction, because otherwise you're going to be outside. Let's say you're going to be on the wrong side of the plane. So we're going to be on the right side of our plane. So z dot product, say, pi s of u bar t minus 1 minus u bar t minus 1. You want this one to be greater or equal than what you get at that point, which is pi s of u bar t minus 1 dot product. So this is the dot product between the vectors. Dot product with the same vector, which is pi s of u bar t minus 1 minus u bar. Right? This is just a fancy way of writing down the algebraic formula for this hydrogen. So this is the vector, the normal vector. This guy, so z dot that should be greater or equal than what you get at this point. This is the half. So if you set it to equality as the hyperplane, and with this direction, it's going to be the half space that contains us. Right? So now, just play xt to be what I call x of ht, and continue. So that. Yes.
That distance function has to be the closest point in S to our V.
That's
right?
the definition of distance.
Yeah. If it was this distance of some fixed point in S, then we couldn't get that. Am I right? It has
I'm
to
not
be.
sure how to even define the notion of approachability for a given point. But do you,
But this instead of set distance of set
so
S.
you're approaching one point.
Exactly.
That's not possible.
That's not possible.
Right. Unless you, for some reason, I think that if the point is forcible.
So what the basically is, you know, S is approachable,
Right.
but the point in S is not necessarily approachable.
But a single point is convex and closed.
Single point is convex and closed, but then you don't have the half space possibility. That's the tricky part, because what does the half space contain? Basically, every single half space that has that should be approachable. So if you can achieve that, so okay, in other words, look at all the half spaces that pass through that point. If you want to approach everything, that means everything
Right.
should be approachable.
Got it. So you need to actually project on that point each time. So to get the half space that is perpendicular
Right.
to your point.
So the point is, if I give you a set S that has non-measured, has a non-zero volume, right? Then if I look at the intersection of all these half spaces, that would be the set S.
For a single point, that's
For single points, just like,
all time.
and you want everything to be forcible, right? So if I move this around, that essentially every point in the RD should be forcible. So it's like too good to be true. All right. Just
Quick question. So the intuition for these to converge is that every sort of convex compact set can be outer approximated with the half space.
that's one intuition, right? In other words, the intersection of all these half spaces is exactly the same. So you look at all the tangents half space.
I think what you said is true for every object that has less than 2 dimensions. Even a line.
Probably, yeah. Right, so anything that has dimension less than D, I don't think you can approach it. I totally agree. Unless something really magical happens. In other words, if your underlying problem is really like a D minus 1 dimensional problem or D minus 2 dimensional problem. Because the volume will be zero, right? So I think notion volume like what we need to catch. But let's not get distracted anymore. So let's think about why that algorithm works. And actually, it's quite easy to see that. I'm just gonna compare the distance of, let's say, u bar t with distance of u bar t minus 1. Right? So let's write down the distance of u bar t minus t and s. So this is definitely smaller than, say, the distance of u bar t and the projection points. Pi s of u bar t. Square distance. Sorry, that's the point I want to look at. The projection of the u bar t minus 1 onto s, which is a point in s, right? So any point in s is going to be only fair. So now let's write this down. So this is going to be the norm 2 of ut bar minus I s of u t minus 1 bar squared. And that's equal to the norm 2 of 1 over t. Okay, so what's this quantity? I can always write it down in the following way. So u bar t is 1 over t summation t prime from 1 to t of u x t prime by t prime. And this is basically right, so 1 over t times the last point plus something like t minus 1 divided by t times u bar t minus 1. So we agree with that statement. This is just the first term corresponding to t, and then the rest, if you multiply by t minus 1, it will be a summation, divided by t will be the rest. Okay. So therefore, I can write it down as the L2 norm of 1 over t, u of x t prime and y t prime. Now I'm going to divide this guy between the two parts. So this minus the pi s u bar t minus 1 plus t minus 1 over t times u bar t minus 1 minus pi s u bar t minus 1. And then I'm going to look at the norm 2 of squares. All right, so let's write it down. So it's going to be 1 over t squared times the norm 2 of u x t prime by t prime minus pi s u bar t minus 1 squared plus t minus 1 over t squared times the norm 2 of u bar t minus 1 minus pi s u bar t minus 1 squared. And then you have a cross term, which is going to be 2 times t minus 1 divided by t squared. And then you have u x, sorry, this is not the primes of t. I don't know why we have t primes of t. Because of u t from here as well, it's t as well. The u of xt by t minus pi s of u bar t minus 1, and this whole thing dot product with u bar t minus 1 minus pi s u bar t minus 1. We are going to get to those terms, but I think the thing that is important is this one. And let me show you a geometric picture again. So this was S. It was u bar t minus 1. And this is my projection. So pi s u bar t minus 1. This is the tangent hyperplane. Right? And what is u? So the only thing that you know about U that is going to be on this side. Okay? So the same picture over there. The U is here. Why? Because I selected XT to respond to this half space. So therefore, U is going to be on the side of the half space that contains S. Right? So now here's the geometric picture. So what is this vector? So this is this guy. Right? So this vector. And then this other vector is this one. So their dot product is going to be negative. Does it make sense? This is why I actually picked that tangent hyperbola. So this dot product is going to be equal 0. So therefore, okay, and what about this thing? This is why I don't think I need actually S to be in L2 ball, but let's leave it like that. I don't know what this quantity is, but at the same time, right, so I can always bound this by and then pi S. Right. So this is in the L2 ball. This is the projection of that point onto S. If I assume that S is in the bond of radius 1, then I'm good because both of these right they have norm to at most 1, and therefore the distance is going to be at most 2, so this quantity is going to be at most 4. But even if you don't have that assumption and you're just projecting something in the L2 ball, right? So if S has a certain property, which I'm not going to go over, then still this is going to be bounded. So for the simplicity, I assume that S is in the L2 ball. So therefore, this quantity is at most 4. Is it clear why this is at most 4? Because this vector is in ball of radius 1. The average of a bunch of things that are in ball of radius 1, so it's going to be in ball of radius 1. And this vector is on X, so it is going to be in ball of radius 1. So this the distance is going to be at most 2, and distance squared is going to be at most 4. Right? Very easy. That is negative, and I mistakenly write this here. I think this is what I wanted to. So this one is at most 4. Definitely this one. This is what I want out. This is at most 4. And what is this quantity? Is that this is the distance of U bar T minus 1 and S by definition of projection. Right. So now if you have a careful eye, you can see what's happening. So if I multiply both sides by T squared, then basically this says that T squared times D2 of UT bar and S is at most T minus 1 squared of distance, and this is distance squared of U bar T minus 1 and S, plus some additive term, which is at most 4. All right. So every time that you see something like this, you should think of telescopic summation. So if I sum this up from T equal to 1 to capital T, then the result would be capital T squared, the last term, T squared of U bar T and S minus something positive, or actually in this case 0, minus 0, would be at most 4 times T. Here's so therefore the distance of U bar T and S would be at most 2 divided by the square root of T, and that's Fenchel. Why? Because this converges to 0 as T goes to infinity at the rate that I wanted to show the convergence. Right? And for those of you that are familiar with, let's say, the convergence, how to show the convergence rate of a first order, let's say gradient descent, this should remind you somehow like something like that. It's not exactly that. Seems to be similar, but it's not really like first order method. I don't see that explicitly. Now, what I'm going to show you that this is actually implicitly running a first order method, but in a dual space. And before, is there any question about this one? Yes.
Doesn't it run it like a gradient descent on the function?
No. Well, so what does that even mean?
Because so D is like a function of U, right?
Right.
If I fix S,
Uh-huh.
I have D of some U and S,
Right.
I want to minimize that.
Right, but then the average of these distances, how it is related to.
Yeah, it just seems to make sense.
No, so it is something similar, but it's actually the Fenchel conjugate of this math that you are trying to mimic. So we will get there. And we can actually discuss offline why that approach doesn't work. But you're often right that if I fix S as an input argument, first input argument is actually a convex function. All right. Let me define online convex optimization first. Yeah, so the weirdness of Blackwell approachability comes from the fact that this is not a loss minimization problem. You don't have additive loss. So you're looking at distance of the average vector with the target set S. But then in online convex optimization, which I'm going to introduce, you will have additive losses. So this is the setup, OCO. It's going to be a full information online learning problem. So we have T rounds. We have an online algorithm, online decision maker, that selects a sequence of actions that we call them A1 to A capital T. A stands for action, and they're all in some set A. And imagine A is convex and closed, and that's it. Yeah. Oh, Marshall, one point about what you also mentioned, which is important. I didn't say anything about A. So in the Blackwell approachability, I didn't even use convexity of A. So even though I added the convexity assumption, you can have a wiki-wacky action set that's not even convex. You need S to be convex and closed, but not A. And then thinking about even projection when you have when you're selecting actions from this set, how would you even define it? You should think of some sort of projected gradient descent, but how can I project onto A? Eventually I have to pick a physical point. That's what makes the problem. If you think about this, these steps are essentially making it further and further from online convex optimization in the primal space. But
It seems the output of action is utility vector.
right, so you
have
can,
to work on the utility sort of.
but that doesn't mean that there is an action corresponding to that utility.
Oh, no, that's
right? So,
yeah.
Right. Okay, so let me continue. So T rounds, you have online decision maker that is selecting these actions. And then there is an adversarial sequence. So there is this adversary that is going to pick sequence of functions. That we call them F1 to F capital T. And you should really think of these functions as the Ft is going to be a function from kernel A, say to 0, 1. And these functions are convex. So they're forced to be convex. So now the game that is played is the following. It's a full information learning game. So for T from 1 to capital T, decision maker selects AT, then observes f of t. It's a full information learning, so you get to see the entire function. not just only the value of the function at the point that you select. So you observe f of t, and incurs a loss, which is equal to ft of at, and the gain quantity. Right? So the goal of the decision maker is to pick a sequence of actions that gives you as small as loss as possible. In particular, we're trying to minimize regret, external regret, which means regret of t for this particular algorithm is defined to be the summation t from 1 to capital T, ft of at, minus the minimum best action concept. So the minimum action concept. So the minimum over actions in curly A, and we are minimizing summation of ft a t from 1 to So you're competing with a benchmark, which is the best fixed action in hindsight, the action that minimizes your total loss given this sequence of convex function. And you're trying to get a loss that is not much larger than this. So you're trying to minimize regret. In particular, you want to have bounds on regret that are self-linear. That would be the ideal goal. Okay. All right, so the next step, I need to define a couple of mathematical constructs related to convex analysis. And then we will have the setup ready for showing you why Blackwell approach will be actually on the come. And the tool that turns out to be helpful is convex duality. In particular, what people called Legendre Fenchel duality or convex conjugates. Let me formally define that. Definition. Fenchel conjugate function. Suppose you have a function x. Doesn't necessarily need to be convex, but let's say it's not convex, a function f that is from, for the purpose of this lecture, from some d bar to r. So D is a subset of RD that is open, doesn't need to be closed, and D bar take of that the closure. It's the closure. I have a function f that maps a d-dimensional vector to reality. Right? Now we define the following function. So f a star of theta, I'm going to define it to be the maximum of theta dot x minus f of x for every x in E bar. So this function is called the conjugate of f. And here a bunch of claims. They're actually pretty easy to show. So claim number 1, f star theta is always convex. Why is that? Does everyone know why f star is always convex? What does this function look like as a function of theta? Just a linear function. Just what you have here. Or an affine function. It doesn't matter that f is some function. If you fix x, this is going to be, as a function of theta, is going to be an affine function. So you're looking at a max of a bunch of affine functions. And this is now the geometry that you need to look at. So you have a bunch of affine functions. And I look at their max. The max is always complex. Okay. What else do I need? I think that's probably just a definition I need for this part of the lecture. Yes. We're going to get back to it later in the second half. But for now, let's just stick to this definition. So let's go with an example. And this example turns out to be helpful when we think about the reductions. So this is the example. My function f of x is defined to be the distance of x in the dimensional space from the set S. But S is a closed and convex. Right? So now, what would be the conjugate functions? The f star of theta would be the max over. Oh, and what is d bar? So I just say d bar is R2. So f star of theta would be max of theta dot x minus f of x for any vector in dimensional space. And I think that this quantity is not equal to the max of theta dot x when you just restrict yourself to set S, and this term essentially vanishes. Again, proof by picture. Right. So imagine you have this S, and somehow your optimal solution is outside of X star. It's called that the argmax X star. So this is the argmax. And then you have this theta some direction. Right. What is wrong with this? So the thing that is wrong is that if I, for example, look at hyperplane with normal vector theta, if I move along this hyperplane, theta dot x remains the same. But if you can somehow move so that you get closer to S, bringing the distance down, this is going to increase this object. So this picture definitely is wrong. And the correct picture, the semi-correct picture is that if you have S, if I look at X star, and I look at this theta, if I go along this direction, I should hit the S at the projection of X star, the pi S of X star. Basically, this point should be the closest point on this half space, on this hyperplane from S. Otherwise, you can always increase this object. Does it make sense? Now, here's the point. So, if I move X star in this direction now, then what happens is that this term changes, this term also changes, but their difference is going to be exactly the same. So this quantity remains the same. Right? Why? Because so if I move delta, this thing is going to be going down by theta dot product delta, and the distance is going to go down by delta dot product theta if I move along just this direction. Therefore, this does not change. So as a result, I can always claim that there is an optimal solution on S. Now, if you have an optimal solution on S, you can just say, hey, I'm looking at max of this point when X is in S. On S, the distance is 0, so this is going to be what you need. Right? It's a useful geometric picture. So this is going to be my dual function. But then it turns out that for this particular function, actually for a general class of functions that we get to them in the second half called the Legendre transforms, there is a duality, meaning that if I look at the conjugate of conjugates, it's going to be the original function. So let me do that. So claim the distance function can be written down alternatively the following. It's going to be the max over all the theta such that L2 normal theta is at most 1. And what I'm maximizing over is theta dot x minus f star of theta. So this time, x is my input argument and theta is what I'm maximizing. Let me show you why this is the case. Proof is quite easy. Actually, I'm not sure if this is easy. It's related to Stein's min-max theorem. If you think Stein's min-max theorem, which is a generalization of the van Neumann min-max theorem that we showed in lecture 1 is easy, then this is going to be easy. Otherwise, it needs a some trouble. So, oops. You know that this is lecture 4. All right, so I want to show that claim. Proof. The distance is equal to that thing, so let me actually start from that. So I'm trying to maximize theta dot x minus f star of theta over all the thetas such that L2 norm of theta, L2 norm of theta is at most 1, or in other words, setting is in vol of radius. Right, so let me open this up. So this is going to be max of theta dot product x minus max of theta dot product y for every y in S. Here I use the first part, what we got here. And this is for all the thetas in L2 ball of radius 1. All right, so now think about this thing inside the max. It's really equal to the following. So it's basically the minimum of theta dot x minus y when y is in S. Right? Because minus of, so I can bring this minus sign inside, that becomes minimum. It's just a constant term, we can bring it in. The whole thing is going to be the minimum of theta dot x minus 1 when y is in S. Right? So now you see a min-max problem. So you're maximizing over theta, minimizing over y, some affine function of x and theta. You can either use a variant of van Neumann. In the van Neumann, I assume the payoff function is linear, but this is affine, still everything is going to go true. Or you can use science if you really want to be obsessed about min-max term, but then you are one of those people that you don't believe that's min-max term. They typically hold in a very general case. So one general case that it holds is this. Stein's min-max theorem. I'm not going to prove that, but I assume that this is true. So the setting is basically the following. So let's say x is in set x, y is in set y. So this is different from the Blackwell approach. You don't get confused. I had this comment in one of the previous lectures that you are reusing the notations. This is just like a lemma within the lecture. So think of it in this way, separately. And then what do I know about x and y? So let's say x is going to be, importantly, compact and convex. So it's going to be closed, convex, and bounded. This other guy is only closed and convex. For example, in cases, I didn't say anything about S being a bounded set, right? So it was just like some convex and closed. S might be unbounded. So in that case, the mean player here is picking a strategy from a closed and convex set that's not necessarily bounded. But then the max fluid is picking a strategy from a closed, bounded and convex set, a compact and convex set, which is the ball of radius one. So now, here's a, okay, so imagine you have this function f from x dot y to r, where f of dot y is concave in the first input argument. So meaning that for any y, fixing y, f as a function of the first input argument is concave. And then f of x and dot is convex for every x. And actually in the original Simon-Max theorem, the concavity and convexity are relaxed to some sort of quasi-concavity, quasi-convexity, which I'm not gonna define here. Just imagine this is convex, this is convex, this is concave. Then this is the theorem by maximizing x in curly x, minimizing y in curly y, f of x and y, you can swap mean and max. So it is equal to the minimum of y in curly y, max in x in curly x, the same. So you cannot always swap mean and max. One direction, which is max mean is less than min max, is always true. That's weak duality. But in order to have the other direction, you need some sort of min max argument to be true. Some fixed point argument should be true. And in this case, it is actually true. Going back to our lemma, so therefore I can swap the order of min and max, and now I'm going to have mean y in S, max theta in L2 ball radius 1, theta dot product x minus 1, y. All right, so now how you can maximize this? Just pick theta to be in the direction of x minus y, but have a normal, probably a normal vector, have a L2 normal one, right? So that means theta star. So if I look at this is equal to theta star dot x minus y, where theta star is just x minus y divided by L2 normal x minus y. Criteria. So this is now going to be the minimum y in S. All right, so what is the dot product? Is going to be L2 norm of x minus 1 squared divided by L2 norm of x minus 1, x minus 1. So this is going to be L2 norm of x minus 1. And that is the distance. So it's the distance of x and S, and hence the distance. Right. So fairly straightforward. Let me now show you what you can do with this. And in particular, back to the discussion I had with Parshan. So we're trying to minimize d of x and s. Let's try to rewrite that somehow using Fenchel duality and see what we get. So this is now kind of a hypothetical scenario. So imagine I'm at the end of the game. So what they call it, thought experiment. So thought experiment. Imagine in Blackwell sequential game, which you want to solve. We output x1 to xt, and adversary or player 2, and player 2 outputs y1 to y capital T. And then we define ut to be the u of xt and yt. Right? So what is the objective function we are looking at? It is the distance of u bar at t or you are at capital T and S, which is the distance of 1 over T, summation T from 1 to capital T, U T and S, right? That's what it is. Then we know there is an alternative way of writing down the distance, which makes it more like a maximization problem. And that's the following. So you're, oh, by the way, let me pick better name for this guy. Definition. If f of x is the distance of x from a closed and convex set S, then they're gonna define f star of theta, or maybe it's the other way. I'm gonna use a notation called the support of the target set. I think it goes usually with the name H. Hs of theta defined to be f star of theta, which is the max of x dot product theta for every x in tas. Right? So I'm going to use this notation for the support of closed and convex set. Then this quantity is basically based on the Fenchel duality proved over there, is a max over all the thetas in B2, 1. And then I need to look at theta dot product with this 1 over T, summation over T, ut, minus Hs of it, right? That's what that thing is. And this is equal to max theta in B1. I'm taking a lot of trigger and stuff, just like the way I understand how this works. So this is 1 over T, summation T from 1 to capital T off, and then theta dot product U T minus H of theta. Let's see if we're all agree. I didn't do anything, so this is just 1 over T times T from 1 to T of the same function. Then we can spread it here. So now, because it's a thought experiment, assume someone tells you, assume you know theta stuff. Suppose you magically know theta star. What is theta star? So theta star is the argmax. So argmax is called theta star. And this is actually an interesting question related to the conversation that we had. So suppose you know theta star. The online algorithm has access to this side information. What would you do? I claim there is a strategy that gets 0 returns. Basically, distance is going to be 0. Finally, it might actually be a negative, whatever that means. So if you know theta star. If you know theta star, then you kind of want to minimize this max, right? But the theta star is given to you, so you want to minimize each step. I claim there is a strategy that guarantees this quantity is negative. Does anyone know what that is?
You're thinking of like theta star is the best response to our strategies, right? Or you're fixing
So
theta star.
imagine this is why I think it's a kind of a hypothetical. So it's not a real setting. Suppose for your strategies that you're going to output eventually, whether it's with that strategy, right? So you haven't yet decided. But suppose so you decide on a strategy And then once you finish, someone computes theta star. And then for the strategy that you are going to play, someone is telling you what theta star is by the first place. Okay? What if that strategy that's under that theta star will give you negative or zero results? That's my question. In other words, if you know theta star, I claim that you can always make this zero. Let's think about that. So this is S. And then I give you some direction, theta star. So my claim is the following. So look at
Can you just put the x in x such that maximizes theta star x, and then ut is going to be that x?
yes. Yes. So I'm going to, exactly. So I'm going to maximize the linear function over S. That gives you some points. So when you think about that, this is going to be a point like this, right? So in other words, imagine this is the hyperplane with normal vector theta star. Move this until it touches S. That would be the point that maximizes theta star dot x for every theta star dot y for every y index. So in other words, if I move this guy, then it gives me this point. Let's call that y hat.
And for any other point, it's going to be negative, right? Inside the parentheses.
Now, you need to come up with a strategy for the Blackwell game. So now I'm going to look at this half space. Let's call that H. And then I know that you started the problem by saying that every half space containing S is forcible, has a good strategy. So I'm going to go with the strategy corresponding to this half space. And let's see what happens. So what is this half space? So the normal vector is minus theta star and passes the point y hat. Right, which is, so you can write down HS of theta as basically theta dot product by hat. Right, or theta star dot product by hat, right? So HS of theta star is going to be equal to theta star dot y hat. By the definition of y hat, is going to be the maximization, so solution of that maximization problem. All right, so now what is the hyperplane? So I'm looking at the hyperplane where, let's say, v minus y hat dot product with minus theta star is greater or equal than I need zero. Right. So if you look at that, then the result is v dot theta star is at most y hat dot theta star, which is equal to h of theta star. So any points in this half space actually have negative for this quantity. Right? And then I know that I can actually, so think of Z as a utility vector in the Blackwell game. So there is a strategy that guarantees my utility vector is UT is always in this half space. Therefore, this quantity is going negative, but this is kind of like best thing you could hope for.
You can pick any strategy that its utility is in H.
Right. As long as the utility vector lands in H, you're good to go. And how we can do that? Because of the hyperplane approachability. So you started the problem by assuming that S is hyperplane approachable or half space approachable, which means for any half space containing S, there's this oracle, you can send the query to get a strategy, and as a result of that, U is gonna land in that half space regardless of what adversary does in that round. That's exactly what's happening. Yes.
I think I got some intuition. So for S,
Sorry, what is it a question?
no, I got the intuition for why the S is forcible. So assume that you could force to go inside S, then regardless of what the maximization problem chooses for theta, you get a negative inside.
Right.
And that's good. But because S is not forcible,
Right.
and then the theta chooser is going second, so it might actually make some of those terms to be positive.
Right. I mean, you don't know exactly the theta corresponding to.
Yeah, but if S was forcible, you didn't even need to know the theta. You
Right.
could always make
You can always make
negative.
all of these terms
Yeah, negative.
zero. You can actually make this term zero.
Even negative, positive, negative.
The distance is well, so it's right. So this can never be negative. You can make it zero because so theta is picked in a way that even though if you know theta, you can make it negative. In the equilibrium, theta is going to make this exactly zero. If F is forcible.
Right.
That's true. All right. So I don't know theta, right? I don't know theta star. Then this seems to not be a good approach. But then imagine somehow magically, not magically, using another algorithm, I give you an estimate of theta star that gets improved over time. Right? So that's now the game we're going to play. So imagine this is the thought. So suppose you have access to suppose theta 1, theta 2, blah blah blah, theta t is given to you somehow. And these are going to be good estimates of theta star, whatever that means. We're going to formally define it. And they are good estimates of theta star. Then you could do exactly the same strategy as before, right? So somehow this is S, you give me a direction, let's say theta t at time t, then I'm gonna just like look at the tangent hyperplane with this normal vector, right? And then define a half space ht, pick a strategy xt that is x of ht, and then my u is gonna be here. So therefore this particular quantity for theta t is gonna be negative. And you can always do that. Right? So therefore, I can guarantee there exists a sequence of x1 to xt such that theta t dot my utility in that round minus hs of theta t is going to be negative. Exactly as before. So for that theta t, I find the point that maximizes theta t dot y by in S. That will be that point. You look at the tangent hyperplane, define the half space and the query to your oracle, get xt, and I claim that in every round you will have this. And this is the equivalent of half space opportunity. As long as you can do this for every choice of theta t, your half space opportunity. Okay. Cool. But again, the problem is we don't know theta t. And that's the part that online convex optimization turns out to be helpful. And let me do the following.
Can I ask a question? Can we say like this last claim that you said is very similar to what we did for follow the perturb leader, because the best response there was like theta t is using actually our last action xt, but then we say that let's imagine we add some noise at the beginning and we use the actions x0 to xt minus 1 as a proxy for actions x1 to xt, and then consider the worst theta that maximizes for x0 to xt minus 1. And we try to choose xt corresponding to that theta.
Conceptually speaking, I think knowing theta star or knowing a sequence of theta 1 to theta t upfront, that is a good estimate, is similar to running the B derivative, which gives you negative regrets. But I think it's at that level. I don't see any other formal connection between Photoshop. Yeah, so there is this guide, which is actually too much of a guide. If it is a good guide, if it's like really close to theta star, you get negative regrets. But that guide, you need to create that guide. So you follow the perturbator, you create that guide by essentially perturbing the historical averages.
I was kind of
So here we are not. So here you need to create a guide a little bit different. And this is exactly what I mean. And this reduction, I think, is actually very smart. So this part of the reduction is quite smart. How you set up a convex optimization or online convex optimization, this is what I'm going to do, that learns status. All right. So maybe it's not that simple. So data is going to be the maximizer of this constant, right? In the layer 2 bar. In other words, it's the minimized layer of the negative of that quantity. And let me now define the following function. So at time t in 1 to capital T, define ft of theta to be what it should be, basically hs of theta minus ut of theta. Right? So why this is adversarial on online learning? Because I have an algorithm, I'm going to decide on xt in the Blackwell. And then depending on my strategy and what the other player does, there will be a UT. So the adversary is looking at both our strategies and generate this function. So now imagine the following online convex optimization. Let me be a little bit more concrete. Learner selects theta t, okay? And then under the hood, when the learner selects theta t, player 1 selects an action in the Blackwell game. So player 1 and 2 are in the Blackwell game. So player 1 selects an action x of t such that theta t dot let me be very specific. So such that xt is equal to x of ht when ht is defined to be the following half space. So it's going to be the half space that is tangent to S and contains the S with normal vector minus theta. So basically, this half space. This is HT. So player 1 selects this strategy. Player 2 in the Blackwell game does something, right? So selects YT. My adversary in the outer game observes this pair. Now, adversary that is playing against the learner adversary selects convex function ft, where ft of theta is equal to h s of theta minus theta dot ut. It's kind of interesting, right? So it's an adaptive adversary. It looks at even your strategy in your round. So you select theta t, so theta t will have an impact on xt. And then the adversary is going to see that together with the strategy of the player two gives you this function. Right? And then they're going to play this game. And this learner is trying to run an online convex optimization algorithm that has a smart brain. All right? So learner runs an OCO algorithm with regret t bound. Therefore, we can say summation t from 1 to capital T, ft of theta t minus summation t from 1 to capital T, ft of any other theta, fixed theta in hindsight. For any theta that is in L2 bar, is going to be a stop, right? So this is going to be bounded by regret of t. And now, let me open this term. Start is easy. Let me just change this to the minimum one. The minimum for all the thetas, not one of theta plus one. And I should mention, so this learner selects a theta in the L2 ball of radius one. So it is an online convex optimization where the learner is picking strategies in ball of radius one, and the adversary is shooting convex functions. And the loss is ft of theta. So now the regret bound is going to be the loss I get minus the minimum loss I could get with a fixed action hindsight in the same region. Right. And what this is going to be. So first of all, we already discussed, right? So for any choice of theta t, so I claim that this is greater or equal than 0 because for any choice of theta t, the strategy of the learner is such that theta t dot ut minus hs of theta t is actually negative. Or in other words, hs of theta t minus theta t dot ut is positive. So this term is going to be positive. So what is this term? Yes.
But isn't adversary choosing theta after we chose ut?
Adversary doesn't choose theta. I'm choosing theta. Learner, the one who is running an online learning algorithm, is actually choosing theta. Then the adversary is choosing the convex function, ft.
But isn't ut known, hs known? So if we choose also theta, so the function is given.
No, so player one, when he's picking a strategy x, he doesn't know why. Therefore, you don't know what is this function. The function depends on u. And u is the vector payoff in the Blackwell game. That is just a function of the two strategies. So I think that the thing that is confusing is that there is a learner and there is adversary for the online convex optimization game. And then there is a player one and player two for a Blackwell. Okay? So learner selects theta t. And at the time that selects theta t, doesn't know function of t. So the learner, you're absolutely right, that can simulate player one and see what x is, but cannot simulate player two, because player two is selected by a second adversary. So therefore, at the time that learner selects theta t, doesn't know this function. It is really full information on the learning. But then after the two players play their strategies, U is known, therefore F is known. And this is why the learner actually observes F. Yes.
It seems X and Y doesn't matter much. There's an interaction between U and theta, right? Learner picks a theta, then in response
Right.
observes a UT. Right?
Correct. You're right. So if, for example, the learner only had seen UT, that was enough. So the only feedback that the learner requires is actually knowing UT, because UT is enough to construct the online convex optimization feedback, which is this function. That's absolutely right. And then one way of doing that is assuming that the learner knows the structure of the Blackwell game and sees the pair of the structure. But maybe the learner could only see that. Could only see just the pair. Yes.
The learner only has the certificate that the UT function is on the right-hand side of HT, right? That's the only thing learner.
Learner doesn't care about that. Learner only cares about minimizing the loss. That's it.
So to minimize the
Yeah.
loss, needs to know that the utility always be in one side of the half space, right? Because
No. I just treat this as a convex function and trying to minimize over time. It's really a primal-dual algorithm.
that's
Maybe I should have said that at the beginning. So at the beginning of the lecture, I called this the primal-dual algorithm because really the learner is a dual player, is playing theta, and then the primal player is player one who is selecting these strategies. And half space approachability is a mathematical analog of the primal player having access to the best response. If you guys have seen primal-dual algorithm for solving games, we already saw that one in lecture one. This is really a primal-dual algorithm in this case, where the learner is selecting thetas, and that's a dual player. And player one in the Blackwell game is selecting actions, that's the primal player. And then they play the game in a way that learner tries to minimize this quantity. And the other one wants to maximize this quantity, actually. Yes.
What, like in that definition, so the theta player is actually hurting us. So
The
why?
player is hurting us.
Because it's maximizing some.
Right, but F is negative of that. So now theta player is trying to minimize, which is the same.
Yeah, I mean, that again, there is hurting us because it's worsening the regret. But my question is, so theta player shouldn't be the same as the one that us, which are the strategy players.
Right, so we are not going to play with theta, we are going to play with XT, that is the best response to theta. That's the point of a primal-dual algorithm. So the one that is generating theta is trying to screw you. But if it learns to screw you, then you're going to land in the equilibrium of the two player game.
since you're doing like not mirror, just gradient ascent in theta.
Right, you're really trying to learn theta star by setting up this dual problem. And if you learn the theta star, which is the, think of it as the min-max problem. So someone is maximizing theta, and then you're minimizing y to get close to s, right? So, and y is basically the average vector. So you are solving that min-max problem by letting the dual player to learn theta and the primal player to select x such that u, the resulting u, is the best response to that choice of theta.
Exactly. So theta player is trying to screw us, and I'm trying to kind of induce you there. But then we said that for any u, theta player is gonna choose the worst case for us, the maximizer for us.
Right.
So, but in order to make that quantity negative, we assume that we know the response of the theta player, and we are now choosing u after knowing it.
Is that the question?
Yeah, in order to make that negative, we assume we know.
What is the question?
The question is that how dare you assume that summation over t is positive, like in the right half of it. Right?
Just using half space opportunity. Give me any theta, it doesn't need to come from a learner.
But you don't see the theta. Theta is chosen by the person who is screwing you.
Wait a second. This is an algorithm that player one is running. So at that time, you know what is theta. So you have a learner is really like a piece of code. So that's the beauty of a primal dual algorithm. So the dual player is something that you have control over. So the actual gameplay is a Blackwell sequential game, where it has a player one and player two. Now at every round, player one is going to send a query to the online convex optimization algorithm to tell player one what is theta t. Receiving theta t, the state drawn from distribution, multiplicative weight, maybe online mirror distance, etc. Knowing theta t, you can invoke the half space approachability to get a strategy such that your utilities on the right side of the half space. That's going to be XC that you play in the Blackwell sequential game. Then player two comes, go with a strategy YT, right? Okay, now XC and YT is revealed to player one. So player one creates a feedback, this function, for the online convex optimization algorithm, feeds that to the function, and then the game runs. Right. So let me finish the proof. So this is going to be greater or equal than 0 because of the half space approachability. And what is the quantity? So let's actually write it down. So it is equal to the max of all the thetas in B2 with the radius 1. What is that summation? It's going to be basically capital T times HS of theta minus theta dot product with summation of ut, t from 1 to capital T. Right? So now divide both hand sides by capital T. This is going to be now equal to the distance of average vector T and S. Why? Because of the Fenchel duality. I'm sorry, I made a sign error. Now it is better. I think I could successfully confuse you in the last step, which is actually the trigger step. Let me do it again. That was correct, but let me actually do it again. So think of this. So this term is greater or equal than 0, so I'm going to replace it with greater or equal than 0 with 0. But about this term is a minus of minimum of something. It's basically maximum of the negative of that thing. So it is max theta in L2 bar. What's the negative of that thing? So it'll be theta dot summation of ut, t from 1 to capital T, minus capital T times HS of theta. Do you agree? It's just multiply it from -1 and then sum from t equal to 1 to capital T. It's a linear function, so theta comes out. You have a summation of UTs, and then this function repeats capital T number of times. Now, if I rearrange the terms, this is basically saying that the max over theta in B2, 1, theta dot average vector UT minus HS of theta. This is at most regret of T divided by T. And now I'm invoking the Fenchel duality, so the max of theta dot something minus HS of theta. This is just the distance of that thing from S. Because remember, this was the conjugate function for distance. It was the support of that S set. Right? So this quantity is equal to 14, is equal to the distance of U, T bar, and S. And therefore Blackwell approachability. Right? So let's actually have a break for maybe 7 minutes, and then we're going to come back and see how we can actually solve online competition. If you have any questions, let me know. So let's continue And I should give you a disclaimer. I'm going to show you an algorithm for online convex optimization called online mirror difference. It's a very general algorithm. I think it's really a genius algorithm. And because of the fact that Nestor was so genius that he could come up with this, it's really hard to give the intuition about why this works in concept. I mean, I can show you the math, and this is what I'm planning to do. But I have worked with this algorithm. I have written papers on this algorithm. I have used it in several papers. But to this day, I don't have a good intuition why OMD works and what's really like at the core of OMD and how it can capture structures of several problems. So I hope you can build that intuition, but I just want to give you that disclaimer because it is important to learn this algorithm. It is the really general way of describing all the first order methods that you know. But at the same time, it's a little bit hard to get intuitions about exactly why it's like. One intuition is gradient descent in this case, in what I call a dual space. But rather than that, I don't think I can give you any better intuition. And there are a lot of subtleties about OMD that if you break any of those, usually the algorithm does not work. And those subtleties make it less intuitive. Oh, and one more reason that why I'm actually going to teach on a mirror descent rather than another algorithm, because it turns out that this is our entry point to a stochastic multi-arm balance. So usually when people talk about a stochastic multi-arm balance, they go with simpler algorithms like UCD, Thompson sampling, etc. I'm actually going to show you an algorithm that uses the ideas that you learned in this class that not only gives you the best instance dependent regret bound for a stochastic bandit, but also gives you the best regret bound in the adversarial case, kind of solves the best of both worlds. All right, so with that, let me introduce this beautiful algorithm, online mirror descent, which is an algorithm to solve online convex optimization in more Java. There are a lot of mathematical setups. Recap of convex analysis. And let me actually do that carefully. Recap of convex analysis. It might not be recap for everyone, so bear with me. Starting from the very first thing I wanted to talk about is the concept of norm and dual. So let's say this is the norm in RD. I assume that everyone knows the definition of a norm. Then definition, dual norm. So the dual norm of some vector x is defined to be the max of, say, theta dot x for all the thetas that the actual norm is at most one. Right. So it turns out that if this is a norm in a linear topological space, let's say RD is also a norm. Example. If you think about the norm 2, then the dual of norm 2 is actually norm 2. Do you want me to show this game, or should I leave these simple things as exercises? Let me actually give them as exercises. All right, that's one example. That's probably all I wanted to say about norms. Okay, so this is an important definition which turns out to be crucial for defining online mirror descent. Definition. Fenchel Legendre or just Legendre transform. Let's say D is an open set in RD, and D bar is this closure, so closure of D. And consider function f from closure of D to R. So f is called a Legendre transform. If the following holds. The condition number one, essentially a strict convexity. So it should be a strict convex in D bar. And it should be continuous. And it's first order partial, basically gradients as a map, which maps points in, say, D to RD should be continuous. Or is continuous. All right, so a three-convex function with a continuous three-convex function with continuous gradient. That's the first condition. And then the second condition is what we call diverging gradient at the border. Basically, if I look at the limits of, let's say, the some norm, pick your arbitrary norm, and actually this appears in the definition. If I look at the gradient, let's go actually norm 2 because I think they're equivalent. If I go with the norm of the gradient of f, this is the function of my points x in RD. So if I get close to the boundary, which is d bar minus d, then this should be plus infinity. So diverging gradient at the border. Let me give you some examples. So example number one. Imagine f of x is equal to half of norm 2 squared. That defines the Legendre map. Example number two, and you'll see in a second that why I'm giving you this particular example. F of x is equal to summation I from 1 to d, xi ln of xi. That's the negative entropy, minus summation of xi, I from 1 to d. So you can check that both of them are strict convex functions. Oh, so here, d bar is gonna be r to the d. And here, I mean, you can think of d bar, d to be, let's say, 0 and plus infinity. You can also think of d to be d-dimensional simplex, which is all it is. Okay. Oh, to the code. So now this is again a little bit of hand wavy stuff, a geometric picture. Think of this is space D. I'm going to call it primal space, which should be here soon. So if you have a Legendre function like that, then if you look at the gradient as a map, right? So what is gradients? Gradient of a function. So the input is a d-dimensional vector, and the output is also a d-dimensional vector. So that defines the map. So if you have a strict convex function that's continuous, and this map is actually continuous, then gradient is going to define a one-on-one map, one-to-one map, from some space D to another space, which I'm going to call it the dual space. D star, dual space. And really, you should think of this dual space as a projection of D using the gradient map. So every point here, using the gradient map, is going to be mapped to some point here. And this map is one-on-one, therefore it has an inverse. The inverse is going to be this thing. So every point goes to gradient, and then using the inverse of gradient go back. And D star is nothing but just essentially all the y's in RD, such that there exists an x in D. I want to keep them constant, such that y is equal to the gradient of f at point. The primal space, the dual space. Here's the lemma, which I'm not gonna prove. So remember the Fenchel conjugates, right? So the recap here. So recap. If I have some function f, then f star of theta is equal to the max of theta plus x minus f of x for every x in, say, D. So that was the Fenchel conjugate. So now this is an interesting lemma. So if f is a Legendre function, Legendre transform, then the following holds. Number one, actually you have the duality for convex conjugate or Fenchel conjugates, which means if I look at the map f star, which is a function from the dual space, no, from somewhere, which I don't know yet, from somewhere to D, so then f star of a star is going to be equal to f. Bullet number two is that gradient of f, as I said, is invertible. And the inverse of the gradient as a map is going to be equal to the gradient of f star. So this guy is basically the gradient of the conjugate function. And think of them as really mapping from RD to RD. So I'm not going to prove that. Leave it as it is. Let me introduce another definition, which is going to give us all the components that we need in order to define on a very set. Before that, let me run this lemma on my examples. If you look at that example, then if f of x is equal to half x squared, then gradient of f is going to be the identity function. F star is going to be again, known too, but this time you have to look at the dual norm. If, for example, it is norm 2, then this is going to be norm 2, because the norm and the dual is the same this.
The dual space should be an unbounded space because of part 2 there. I think.
But so, well, so, right, so if, right, so exactly, so the dual space, because if X converges to the border, then the gradient is gonna diverge. Somehow, you should definitely have points in the dual space that they have infinite norm.
I was trying to say it will be convex.
Yes. Right, and thank you for mentioning that. This thing needs to be convex also. So in my definition, everything should be convex. So this should also be convex and open, so the convex and closed. So this is convex and open. And this is going to be convex and open. And unbounded if you have a Legendre term. Then we continue, the f is norm 2 divided by 2, then this is going to be identity function, this is going to be this, and the gradient, the inverse of that, which is the gradient of f star, again is going to be the identity function. So therefore, this Legendre map is transforming, let's say, RT to RD. So because gradient is identity, so it can transform RT to RD. In my second example, when f of x is equal to summation xi ln of xi minus summation xi, negative boundary entropy minus the linear term, then the gradient of x is basically log function. So you apply the log to every coordinate of x, and you put them together. So ln of x1, ln of x2, all the way to ln of xn. The f star is going to be summation, if I'm not mistaken, summation over I e to the power xi. That'll be just an exponential function. Yeah, I think that's true. And then the gradient of f star is the exponential function. It's the So one more component, and then we are going to get to the definition of the algorithm. So definition. What they call Bregman divergence. Have you guys seen Bregman divergence or callback neighbor divergence before? So let me formally explain that. Say f is a Legendre function. Then the corresponding Bregman divergence defined by df of x and y is a notion of distance. But it's a weird notion. It's not symmetric. Well, so it does not satisfy the triangular inequality exactly. It satisfies some version of Pythagorean theorem. So everything that you have in mind for traditional geometry, there is a variant of that when you think about Bregman divergence, scalar labor, etc. But you should forget about those intuitions. Well, don't forget about the intuitions, but do not assume that all of those intuitions are correct. In particular, you can't always swap. Sorry, so let me go with the definition and then I'll tell you the comments I have. So the distance, so for every 2 points x and y in, say, d bar in the space that corresponds to that Legendre function, this is equal to f of x minus f of y minus x minus y, these are vectors, right? x minus y dot product with gradient of f upon y. Right? So some corollaries that are quite simple. This is always bounded. In particular, it is strictly greater than 0 if x is not equal to y, and it becomes 0 only if the two vectors are the same. Why that?
Strictly convex.
This is a strict convexity. If it was greater or equal than 0, it was convexity. But why? This is y, this is x. So f of x minus f of y is this height, and that's x minus y dot product gradient. So this is basically taking gradient at y. So this quantity, right? So x minus y times the slope of this line is 1. Right? So this is greater than that, therefore it's greater than that. And it is strictly convex, so therefore, as long as x and y are not the same vectors, it's going to be strictly greater than 0. And for example, if f was strongly convex, then you could even say this is greater or equal than, let's say, a strong convex in norm 2, and this alpha strong convex, and it's going to be at least half of alpha times x minus y squared. But for now, we don't have the assumption of strong convexity. It's just like a strictly convex function, so it is a strictly greater. Just a bunch of disclaimers. This is unfortunately not equal to that. Always, there are some cases that they're equal, but not always. There are a couple of lemmas. I'm going to get to them next. But before that, let me go over my examples. If f of x is equal to half of norm 2 squared, then the Brakeman divergence between x and y is basically half of the L2 distance. So this is the L2 distance between x and y. Half of L2 distance squared is going to be the Brakeman divergence. If f of x is true negative entropy minus the linear term, then Brakeman divergence of x and y is what people call general like KLR. It is the summation over all I, xi, ln of xi divided by yi, minus summation of xn. And this is actually an example of the asymmetry. So if you swap x and y, this is not coming. Cool. So let me go with two simple lemmas about Brakeman divergences that we are heavily using. Can I erase this one? Any questions? Because this part is a little bit drier than the rest of the lecture, so stop me at any point if you have questions. I'm happy to explain. It's going to get more interesting when I talk about the algorithm. So, two useful lemmas, or do I have three? Oh my God, I went so fast. So, two useful technical lemmas, and I'm gonna emphasize on useful because every time that you see a first order method that you want to analyze, keep these two lemmas in mind. They're gonna be definitely essential in analyzing the first order. So two useful technical lemmas, lemma number one. I'm going to actually prove both of the lemmas. So I'm not sure if it's a lemma, it's just an identity. So for any three vectors, x, y, and z, in, say, closure of D, we can say df of x and y plus df of y and z, so xy and then yz, is actually equal to df of x and z plus, right? So x minus y dot product with gradient of f at z, gradient of f at z minus gradient of f at y. Let's memorize it first, because I think it's helpful. So you have x to y, and then y to z, and then it's going to be x to z here, and then this extra term is x minus y and z minus y, but then the x minus y part is going to be as it is. For z minus y, you have to apply the gradient. Enough? The proof is just the definition, writing down the definition. We'll actually do that further. So df of x and y is fx minus fy minus x minus y dot gradient of f at y. Df of y and z is f of y minus f of z. And now you already see the cancellations. If I add them up, this cancels with that one. So minus y minus z times the gradient of f at z. And then df of x and z is going to be fx minus fz minus x minus z, the dot product with gradient of f at z. Cool. So add them, subtract this guy, then all these terms cancel. So fx cancels fx, fy cancels fy, fz cancels fz. What happens after? So look at these two terms first. If I'm subtracting this with that, so the z dot product gradient of fz cancels, and you get x minus y dot the product with gradient. So here I get x minus y dot product with gradient of f at z. And here I have minus x minus y gradient of f at y. So that's going to be x minus y, gradient of dot product with gradient of fz minus y. So here it's going to be minus x minus y, gradient of f at y. So if I add them up, it's going to be equal to x minus y dot product with gradient of f at z minus gradient of f at y. And that's essentially the proof. Quite easy. So lemma number two is what I call the Pythagorean theorem for break-on divergences. So lemma number two. Let me start with the geometric picture first. So this is the geometric picture. Imagine you have some space A, which is a subset of B bar. And you have some points in this space A, and then you have some points potentially outside of this space. Let's call that X. So you find a point in A that has the minimum. So A star is the arcmean of A and let me call this. Right, so this is X, this is X, and I call this guy maybe A prime. Yeah, fine with A, but that might be a little confusing. Right. So I have X, so I find a point in this set that has the minimum Brabant divergence between that point and X. And so when you think about this, so fixing X, this function is actually convex. Why? So fixing, in this case, Y, right? So this is constant, this is linear, this is convex, so therefore this thing is going to be convex. So it has a unique optimal solution, so therefore every time we say ASR is equal to R of this thing, actually there's a unique solution. You should really think of it as a projection using Bregman divergence. You have a point X, you're projecting into this set A by solving this convex minimization problem. This can give you this point A star. And now this is my version of Pythagorean theorem. It says, let me write it down. The Bregman divergence of A prime and X is at least, sure, I make a mistake. Right. Is at least, if I go from A prime to X, A star first, which is EF of A prime and A star plus A star and X.
Should it be reversed?
Of course not. Because I could pick A prime to be A star, and then the distance of these two is 0. So right, so
I'm thinking on a special case, like the Bregman divergence is norm 2, so it becomes the regular triangular.
right. So that's
So it means that A prime and A star plus A star and X should be at least A prime and X, which is the reverse of it, right?
no, but if I look at that, the special case. Why in the special case is not true? Well, so Mohammed, this is not norm 2, this is norm 2 squared,
Oh, I see.
right?
Yeah,
So
okay.
you should really think of it as Pythagorean theorem, not
Triangle.
triangular inequality. So even for norm 2, this is correct. All right. Do you want to see a proof of this? It's actually easy. I can go with the proof. Should I go with the proof? I think I can prove it for norm 2. Yeah, fine. Let me go with the proof. I actually use number 1. And that's the yeah. Right, because if they come in a star X, this is why I tell you that this is actually all the useful level. So df of A prime A star plus df of A star X minus df of A prime X, which is the right hand side minus the left hand side of this thing, will be equal to A prime minus A star dot product with gradient of F at x minus gradient of f at s. Mistake. Yeah. Right. So the point is a prime minus a star is actually direction inside the set, because this is on the border, this is inside, so this is going to be direction inside, right? And the second observation is that look at this convex function when I fix y. So if I fix y, and just again as a function of x, what is the gradient? It's going to be the gradient of f at x minus gradient of f at y. Is it clear? This is a constant, it vanishes. There is a y dot product gradient of f at y, again that vanishes, the gradient. So I think my point is gradient of the of x y when x is greater than the variable is the gradient of f at x minus gradient of f at y. Right. So this is basically saying that, hey, I'm looking at the direction x minus a star. Sorry, I'm looking at, right, so this is the gradient of the function of the optimal solution. So if the gradient of the function of the optimal solution, dot product with this is not positive, if let's say it is sorry, if it is positive, then I could move along this direction and make the objective function. So we're going to say this is negative, right? So a prime minus a star is inside. So this is kind of like the grad. Oh, so this is the inverse of grad. Sorry. So this is the negative of the gradient of perpendicular divergence at the optimal solution. Right? X was the constant. That's a little bit confusing. The x part here is the constant part. A star is the optimal solution. So we found a point such that the negative of the gradient is this, and the negative of the gradient, if multiplied by this point, is positive, then you're in bad shape, because that means the gradient dot product with this was negative. So you could move a little bit along this direction and make the objective function small. It's a minimization problem if this direction, so in other words, the minimization problem if this direction is, if dot product of this direction and the gradient at this point is positive, then you're in trouble. So if it's a negative, you're in trouble because of the minimization problem. But again, so if you pick another point inside the convex set, I connect that to a star. I look at the gradient of breakpoint divergence when x is fixed as a function of a. So if that gradient dot product with this direction is negative, then this is bad. Because if that's negative, it means you can actually move along this direction and make the objective function smaller. So the gradient at that point, which is, so therefore, my conclusion is that the gradient of f at a star minus gradient of f at x, which is the gradient of breakpoint divergence at the optimal solution, dot product with a prime minus a star, it should actually be positive. Or greater than that. And therefore, this thing is negative, and hence the proof. It wasn't as conservative for this. All right, so we have everything to tell you what the algorithm. Before that, let me actually introduce two other algorithms that I hope one of them you have seen, and I'm pretty sure the other one you have seen because I actually taught it in the class. examples of some algorithms. Algorithm number one is what I call OGD, online gradient descent. So this is what the algorithm does. You initialize at some point W0, then for t from 1 to capital T, we're going to say WT plus 1 is equal to your action in the previous round, AT. So select action A1, so that's initial point. Somehow pick the first action. Then you get to this time, say WT plus 1 is equal to AT minus some number, I'm going to call it learning rate, times the gradient of, you're running an algorithm for online convex optimization, recap of the setting, recap. So you're selecting action day 1 to AT, that's the algorithm. And then adversary is selecting this convex function of 1 to F capital T. That's the adversary. Right? Okay, so I'm gonna look at my previous action minus, because I'm minimizing eta times the gradient of f of t at the point AT. But this guy might be outside of this action set A. That's what this convex compact says. So I'm gonna say, well, so AT plus 1 would be the pi. We had this projection operator with respect to L2 norm of WT plus 1, which is basically arc mean over all A in A. I'm minimizing the L2 distance of A and WT plus. Right? So that's the first algorithm. It's called projected gradient descent, online projected gradient descent, online gradient descent, Zinkevich algorithm, they're all this. And then you can run it in an arbitrary action set. The second algorithm, let me actually write it down. For the second algorithm, I assume my action set is actually delta D. So it is a D-dimensional simplex, which means pick up expert, best expert problem. So I have D different options, I'm going to pick one of them. And it can be a mixed strategy. So A is going to be delta D. Again, I'm going to select some randomized strategy A1 at the first place. Then for T from 1 to capital T, first let WT plus 1 to be equal to AT times e to the power of minus eta gradient of ft at point AT. And then once you did that, you might not be a distribution anymore. Remember, so you have to pick points in a d-dimensional simplex. So I set AT plus 1 to be WT plus 1 divided by norm 1 of WT plus 1. I'm normalizing so that the summation of the numbers is variable. It is important that the initial action you pick is all positive, therefore you remain positive. So this is going to give you a feasible point. So at the initialization, maybe I go with action A1, which is 1 over D, 1 over D, all the way to the end. Do you guys detect this algorithm? How we have seen it before in this class. That's hedge. Look at the special case where f is a linear function. So therefore, this gradient is just like some loss function LT that is fixed. It's not a function of your action, it's just a loss function. sorry, it's a function of reaction, it's a dot function dot product AT. Right, so if, right, so if, let's say ft of AT is a linear function, this LT, or ft of L is LT dot product A, then if you take the gradient, right, then what am I doing there? The single variable function. Right. That's true. So, right. So, exactly. So, if A is a distribution and then you take derivative, then that's going to be vector. Yeah, I confuse myself. This function that is mapping from RD to R. Right. Just a bad notation. So what I meant is the gradient dot product is all one. Right. Yes. You don't do it. Yes, I think okay. So if I do coordinate by coordinate, there's not more here. So this is basically what I meant. WT plus 1I is equal to ATI times e to the minus gradient of FCAT at coordinate I. Okay, that's the correct version. Right. And then if it is a linear function, this is basically just the coordinates I of LT times A at that coordinate. And that's exactly what we had before. All right. With the caveat that I never wrote it down using exponential function, we were always multiplying the 1 plus eta to the power of the loss. But that's the equivalence, just like not the same way. Yes.
Why are you multiplying the action to that exponential?
Right, so that's exactly what we were doing. So we had these, we were keeping track of these weights, and then based on the loss corresponding to these weights. Yes. So these weights are the weights that you're keeping track of, but then you have to normalize it to have actually an action. Right. So now we see the more general version of this algorithm. And that brings me to unlinear descent. So here's what unlinear descent does. Again, a geometric picture. Let's say some iteration, this is D bar, you have some actions, say AT at this round. And from AT, you want to get AT plus 1. Let's look at the dual space and do the following. So first, apply the map that brings point from the primal space to dual space, which is the gradient of the Legendre transform. And this algorithm is going to be parametric with this Legendre transform F. So F is something that you as a designer pick, given that F it defines the dual space, the primal space, the dual space, and now you have points AT after the map gradients. So this will bring you somewhere here. Let's call that gradient f of AT. Right? So don't get yourself confused. So this gradient is different from this gradient. This is for the objective function. This is for the map that you use in the algorithm. Right? So it's just like some point in the dual space. Now I'm going to do gradient updates exactly as in gradient system. So I'm going to move along the reverse the gradient minus eta gradient of ft at the point AT. Right? That gives you a point wt plus, not the wt plus one, some points. That is going to be the gradient of some point, because every point in the dual space, if after this move you remain in the dual space, then every point can be written down as a gradient of something in something. So something in primal space for sure. And to complete the picture, so this is the primal space, but the action sets that you're setting action is just a subset of that, right? So this is my action set. I had this action in the previous round, AT in my action set, gradient brings it to dual space. I do the gradient update with respect to my loss function, the convex loss function. Now I have a point here. If I am in the dual space, it should be you should be able to write it as the gradient f of some point. I'm going to call it wt plus 1. And therefore, if I apply the inverse of the gradient map, which is equal to the gradient of f star, as we know, it's going to bring it somewhere here. And that somewhere is the wt plus 1. But we always want to pick an action that is feasible. This is set A. I'm going to project it into this set. And that's the AT plus 1. And how am I going to project it? Using Bregman divergence, exactly as we had before. So AT plus 1 would be the argmin of A and wt plus 1 for A's in set A. So that's the pictorial description of unaware descent. So you start from a point in your action set, a physical point. You apply the gradient map such that gradient map will set to your Legendre transform such that you go to the dual space. Then you move along the direction of the gradient. Algorithm is going to be well defined if this point is in the dual space. If it's not well defined. So you need to always check this consistency. If it is a dual space, there is a point in the primal that maps it here, pick that point, and now project it using Bregman divergence into the origin actions. Yes.
What's the gradient direction? You mean gradient of what? There?
The loss function at that time, at the previous action. So you have your in the online
So it's not that-
convex optimization.
So it's not that we have a utility function in dual space and we are running gradient descent on that utility
No.
function.
No, so your after all, there is no utility function, it's a loss. So you're trying to minimize loss. The loss function in that round is ft. And so you play action AT, you observe this now, you want to update your action. Compute the gradient, which is going to be a vector at the point AT, and then run this recipe. All right, so this is the cool part. If f of x is equal to half of x squared, and d is r to the d, then this is actually OG. This is only gradient descent. Why? Remember, so for this particular Legendre function, the gradient map was identical. So nothing happens. So AT maps to AT, we do the gradient update, then nothing happens, but the bytes come out of A, then you project back. So gradient update, projection. Now if f of x is equal to summation of xi, ln of xi, minus summation of xi, what was the gradient now? It was the log function, right? So let's say, so you apply the log function, then you add the gradient, then you take an exponent, right? So what does that mean? So somehow I'm saying ln of wt plus 1I should be equal to ln of at and I. These are our vectors, but I'm looking at the coordinate I, minus eta times gradient of ft at the point at, but coordinate. This is this identity. But now take a log. So we have a lot, take an exponent. So this is equivalent to saying wt plus 1I is actually equal to ati times e to the power minus eta gradient of ft at the point at of the coordinate. Now, if I set D to be D-dimensional simplex, and this is my F, therefore the Bregman divergence would be the generalized callback labor divergence. Actually, you can show, given any points like this, if I'm defining a T plus 1 to be the argmin of that Bregman divergence, the callback labor divergence, when I'm minimizing this over D-dimensional simplex, I leave that as an exercise that this is going to be exactly equal to the normalization factor, which is Wt plus 1 divided by L1 normal. I leave this as an exercise. It's actually easy. The proof is similar to the argument I had here. Let's look at the gradient. The direction of the gradient should always be for the optimal point. The gradient at that point should have a direction that's towards the inside of the convex set. And once you write that down, it turns out that for this particular choice, is equal to the dot product is 0. And that's the optimal solution. All right. So everything is alignment resistant. The people in optimization, they usually say, so no, I think I agree with that. And then the interesting part in analyzing this algorithm is actually quite easy. So when you write it in its most general form, the analysis becomes even more straightforward. You might have seen an analysis for OGD, BRD analyzed multiplicative rate update using a potential function argument. But really, like all of those analyses are the one that I'm going to show you in this case, and this one is the shortest. I think I can prove the theorem I'm going to write down. I'm not sure if I can get the bounds in the remaining time. If you guys stay longer for 5 minutes, I probably can write down the bounds as well. And you see that we get exactly the same bound as we got using the direct algorithms. All right, so theorem, which is due to Nestrov. If F is a Legendre transform, and unlinear descent is well defined. So I'm adding this step because not always unlinear descent is well defined. But in these spaces, in both of these cases, the dual space is going to be RD. So it contains everything, unlinear descent is always well defined. But not always unlinear descent is well defined. And the moment it is not well defined is when you add a vector, you might go outside of the dual space. But it's very unlikely that happens. Why? Because this space is unbounded. So if you have a compact closed set and it's unbounded, if you make a slight movement, you should still remain in the same set. With the caveat that sometimes it's gradient divergence. So the moment that the gradient diverges, at that action, you might end up outside of the dual space. But if that does not happen, OMD is always valid. There are pathological cases in which you can mess with the algorithm. I learned one of the pathological examples last night for the first time in my life. I have always assumed that this is OMD is always well defined. I realized actually it might not be always well defined. And I was planning to tell you that pathological instant, but I'm not going to do it in the interest of time. Let me just give you the positive result. So if the OMD is well defined, then so the setting is the convex optimization, regret. Oh, and I need to add, I didn't tell you what the algorithm is. I didn't write it down. Let me actually write it down for me. Because the initialization step is important. So initialize by selecting action A1, which is a specific action, and it's important that you pick this specific action. Arg of f of A, minimizer of this convex function, the mirror map for A in A. After that, for T from 1 to capital T, so I'm gonna define WT plus 1, basically in a way that gradient of f of WT plus 1 is equal to the gradient f of AT minus eta, the gradient of ft at point AT. That's the gradient of update here. And then the breakdown projection. AT plus 1 will be the minimizer of the breakpoint divergence between A and the points W T plus 1 for every A in that's the one. I mean, you can write a fancier version of it by saying, hey, WT plus 1 is the gradient of F conjugate of this thing, but it's really like, now, if I run that algorithm with that initial choice, which is important, you pay attention here. Here it wasn't that much important, but all 0 is going to be the best one, and here all 1 over this is going to be the best one. This is the one that minimizes the negative entropy or equivalent maximizes the entropy. So regret at time t is going to, which is equal to the summation t from 1 to capital T, ft of theta t minus best actions ft same thing, ft at, fta. Is it that most, given learning parameter eta, learning rate eta, and f is going to be equal to at most 1 over eta times max, or maybe sup is better, supremum of f of A over all A in A minus f of A1, that quantity over there, divided by, I already have eta here. Let me actually separate them because later they'll play different roles. So the first term is what people call initial divergence. Somehow the maximum amounts that f of x can get for 2 physical actions. F of x minus f of y, the maximum amount of f of x minus f of y for any 2 physical actions. And then the second term is 1 over eta times t from 1 to capital T, the f of AT and WT minus the f of AT and WT plus 1, and then AT plus 1 and WT plus 1. So those hardcore optimization guidelines, as I say, they call this initial divergence. And they call these things local mode. Next time that you heard these terminologies, this is what they refer to. And okay, so this one, you can imagine this is gonna be bounded, it's nice. This one is not clear, but we will see that this one is also gonna be bounded once you add assumptions on your convex. But before that, let me actually show you this method here. And this is the one that I think you should always remember when you're working with unlinear relations. The rest is just algebra. From this, how to get the rigor bound is an algebraic step, but this part is really where the crux of analysis is happening. Proof. And proof of that is actually quite easy. I'm just using the two technical numbers I told you, and that's it. Let's write it down. So I'm gonna go term by term. So ft of at minus ft of a, right? So this is a convex function, and we can always say this is at most at minus a dot product with gradient of ft at the point at. Why? Because again, so this is at, this is a. So this difference times the gradient at this point is like a slope of this line times this difference. It is more than how the function goes down. Convexity, the convexity of ft. And this is literally the only step in the analysis that uses convexity of f. If you're wondering why we don't have online non-convex optimization because of just this step. If you manage to have this step working somehow, then the rest of the analysis goes. But it is pretty much the definition of convexity. All right, so what is the gradient? So you can write it down using the primitives of the algorithm, at minus a dot product. So this is the gradient map applied on w t plus 1 minus the gradient map applied on at divided by eta, but you need to change the sign because it's a minimization problem. I'm gonna apply the sign change here. So it's gonna be equal to 1 over eta a minus at. I'm just like rewriting the whole term. Gradient f of w t plus 1 minus gradient f of. Is that correct? Right.
That should be plus, right? Gradient of f of w plus.
Why?
No,
No, that's not a very sense.
nice.
That is correct. And was a minus a minus a. Seems correct. Right. Good. I'm gonna find an upper bound in this term. Right. I think it's good. So now this is the part that I'm going to use one of my useful lemmas, lemma number 1. All right, so let me see if I can do. So this is equal to something that only has Bregman divergences. This is equal to x minus pi. So df of a and at plus df of at is equal to minus of that. Right. df of a and at plus df of a t and w t plus 1 minus df there you go minus df of a and wt. Remember this. AAT, ATWT plus 1, and then you have AWT plus 1 subtracted. So this is going to be A minus AT dot product with gradient of F on WT plus 1 minus gradient of AT. This is exactly the same. Cool. What else? Let's think about this term. The A is here, WT plus 1 is outside. A is just like some point inside. This is A, the carry set A. And the projection was AT plus 1. Now my second useful lemma says it says df of A and WT plus 1 is actually at least df of A and AT plus 1 plus df of AT plus 1 and WT plus 1. So this is the minus of that quantity, so it gives you an upper bound. And if you write it down, it's going to be 1 over eta, the first two terms as they are, df A and AT plus df AT and WT plus 1 minus, now I'm going to use this two, minus df of A and AT plus 1 minus df of AT and AT plus 1 and WT. And you're almost done, right? Why? Because now if you have a careful eye, these two, they form a telescopic term. If I sum them up from t equal to 1 to t, only the first one and the last one will survive. We can do that. Give me maybe 4 or 5 minutes, I will be done. Right, so therefore, that term, sum t from 1 to capital T, is going to be 1 over eta, so regret, and T is going to be at most 1 over eta times df of A and A1 minus df of something, which is A and A T plus 1, whatever that quantity would be, I don't care, plus 1 over eta times T from 1 to capital T, df of W, AT and WT plus 1 minus df of AT plus 1 and WT plus 1. But this is the second term we're going to show. What about this term? So I'm going to say this is at most 1 over theta times what is the df of A and A1? So it is f of A minus f of A1 right, so I think the other term is going to be negative always. Minus A1 times gradient of A1. Right. So this is always going to be negative. And the reason is because A1 was the minimizer of time. right? So remember, A1 was the minimizer of F, so therefore the gradient of F at A1 dot product with A minus A1 should always be positive, therefore minus of that should be negative. And that's essentially the. Okay, so now this is upper bounded by 1 over theta, the supremum of Fa, of course, A in A, minus F of A1, the initial divergence, and then plus 1 over T, sorry, 1 over eta, sum over T, the local node, CL, AT W plus 1, minus DL, AT plus 1 W. I can show you why this is ordered 1 over square root of T. Let me write down the statement. I can leave it as a simple exercise. It's really like simple, just working with this term is quite simple. Suppose the following is true. Number one, f of x is alpha strongly convex. For example, if I look at f of x to be half x to the squared, this is one strongly convex. The second assumption is that if I look at the gradient of f, the dual norm of this guy is at most g. And then the third assumption is that f of a, let's say f of x minus f of y, is going to be, in absolute value, is going to be at most r squared for any 2 points x and y in A. So somehow the initial divergence is bounded by this R2. The gradient, oh, this is not, this is, none of the functions, they have the gradient that is diverging that much. So the norm, so all these convex functions, they have bounded gradients in dual norm. And then, so 1 and 3 are constructs that are in your control. Meaning that you can pick a function f in your algorithm that is strongly convex. For example, you can pick L2 and a function that if x and y are changing in your action sets, it's not changing that much. But 2 is an assumption. Then under this, the regret bound, the right-hand side that I have here, is going to be upper bounded by RG, I believe the square root of, I don't write it down exactly. Right, so R squared divided by eta. R squared divided by eta plus t times eta times g squared divided by alpha. Something like this. And then set eta appropriately. I think this gives you something like RG square root of alpha over t. Let's assume this is true. This is actually pretty good. Just play with this term, we do that functions right about it. I'm gonna add a note on the website. Sure. But then let's actually go back to our Blackwell approachability problem. And see if I run this algorithm with this guarantee, what do I get? What is R? Say I'm using norm 2. What's going to be R? So remember, x and y are going to be the theta that in the primal-dual algorithm we're using. Remember, so in solving the Blackwell approachability, we have this learner that's picking the directions in ball of radius font, theta t's. So X and Y are 2 points in ball of radius font. If, for example, f itself is L2 norm divided by 2, then these are numbers between 0 and half. So R is 1. R for our Blackwell approach problem is going to be 1. What about G? So ft theta, just as a recap, it was hs of theta minus theta dot x. And this hs is just a maximization of theta dot y for y in s to recall. So it's something if you look at the gradient of this guy, it's going to be theta dot product with two difference of 2 of them are in L2 bar. Then you can use maybe Cauchy-Schwarz or Holder inequality, and as a result, this is going to be bounded by basically the L2 norm of 2 vectors x and y with L2 norm of theta. So this is bounded by 1, this is bounded by 2, so G in our problem is going to be 2. And then again, if I use norm squared, this basically around online gradient descent, alpha is going to be equal to bond. So therefore, you get 1 times 2 times the square root of 1 over t, which is essentially the square root of 4 over t. Pretty much similar to the other we get. Yes.
That's gonna be a square root t over alpha.
Oh, so this is total regret. What I meant was that if you divide by t,
So then alpha is in t now.
you are right. Alpha is here.
And that's gonna be average.
That's average regret. If I'm going total regret is like it is, and therefore average regret divided by t going to the utmost RG square root of 1 over half. I think you're right. Yeah, so alpha larger is better, which should go bigger knowledge. All right, sorry I went a little bit over time. The only thing I didn't prove is how from this bound, given these assumptions, we can actually get things. I'm gonna add a note on the website to make sure that we all know how to prove this step. Quite easy though. All right, thank you.